weird. Oh man, now what did I do? Record, I just haven't figured out what it is. Alright, so the final. Just like the midterm, it's going to be closed everything. So it's not comprehensive, meaning that what I'm actually intending to test you on is the stuff since lesson 4. Yeah, since the first midterm. So, well, since the only midterm. The midterm was lessons 1 through 4, or assignments 1 through 4, which was in the book actually chapters 1 through 5, right? So this will be assignments 5 through 9. Of course, you may need to know some of the stuff from the first part of the course, but that's not going to be the focus of the class, of the test. So I'm just going to try to give you an idea. Do you have a question? Sure. You will not have a programming assignment on sorting. There will be stuff on the final about it, and if I get my act together enough, I might put together a little suggested assignment, not programming assignment, but whatever I do on the final isn't going to be a programming assignment, a programming question about sorting. It'll be to see whether you understand the sorts. Yeah. So let me just start at the beginning. I could see, so templates would be the first topic. And I could see myself putting a question maybe where I write a really, really small class and have you just convert it to a templated class. Okay, that would be something I might do. By the way, I guess I should just say that I'm not guaranteeing that everything on the final is going to be something that I mentioned right now. I'm just kind of trying to give you an idea of, when I think about what are the important things to look for and what might go on the test, this is what comes to mind. And then for iterators, I would say you would not be responsible for the actual iterator classes themselves. Like, I'm not going to ask you to reproduce that or something, reproduce the times operator, or I guess I should call it the dereference operator or the plus plus operator for iterators, but I could ask you to implement something similar to like the insert or remove current member function that had to deal with the iterator. So you might have to use like the i.link thing.
Remove current, or what was the other function?
Insert, right? Or was it attach? It was attach, actually.
So it's attached?
Yeah, I think it was attach. And I realized that those were conceptually pretty difficult, so I would try to be kind about that if I put something like that on the exam. But they weren't really long, right? What's that? Yeah, they were just like 6 or 8 lines or something like that. So. Maybe iterator, like, and if I did put something like that on there, I would probably need to actually provide a copy of the iterator class for you. I would provide a copy of whatever you need, so you don't have to memorize like the link function and whatever. And then I could also see myself asking you to write maybe a little bit of client code that uses an iterator on a class. And that's actually fairly important, right? Because that's actually the most likely thing that you'd actually be doing in real life, right? is maybe using the STL or some other package and using the iterators there. Okay, so I think after that was stacks and queues, and I won't test you on stacks and queues on the final. Not that that's not something that you'll be expected to know in the next class you take, but I'm going to narrow it down a little bit for you. So after that was recursion, I believe. So I could see myself putting, having some sort of recursive question, where you just, write a recursive function. Then we had trees. So I could see having you write a function to do something with trees. I would limit it to binary search trees. I might also ask you to tell me something about a pre-order traversal or a in-order traversal or a post-order traversal. So if that doesn't sound familiar, make sure you look that up.
Post-order, what order?
Pre-order, in-order, and post-order. And I'm looking for that section in the text right now. I kind of talked about this a long time ago when we did in the stack lesson, actually. But in the chapter 10 of the text, there's a section on tree traversals. So it talks about pre-order traversal, in-order traversal, and post-order traversal. So I could see myself giving you a picture of a tree and asking you to tell me what the order is if you do a pre-order traversal or something like that. I could also see giving you a list of numbers that are going to be inserted into a binary tree and having you draw a picture of the tree. Binary search tree. Did I say binary search tree? No, binary search tree. Okay, and then so basically in the trees section, I'm really focusing on the binary search tree thing, in case you hadn't noticed. All right, after trees was inheritance, right? So I could see maybe I give you a base class and ask you to write some or all of a derived class. You should I think one of the important things about inheritance is to understand the different situations you can be in when you write the base class, the different types of functions, like the ones that can't be overridden and the ones that might be overridden and the ones that have to be overridden. No, may be overridden, but if you do, you need to call the base class version somewhere in there, and then the ones that absolutely have to be overridden. So just kind of be aware of those different types and know how to implement them. know, understand polymorphism, right? Virtual functions, maybe what's the output of this when there's no virtual? What's the output of this when there is a virtual? And then sorting and searching. I would expect that I will probably have a question where I give you a list of numbers and say, show me what the array is going to look like after each pass if you use bubble sort or if you use quick sort. I also want you to know the big O analysis of the different sorts. Okay? I think that's probably it. Okay? Any questions about the final? Okay. So let's get back to sorting. At the end of class last time, I was doing bubble sort, and here's what we had there. Slightly different. I think what we ended up with last time, I actually had a for loop here. So I changed it to a while loop, which I think is better, and I think that's the only difference. But rather than actually run this now, I'm going to run them all, excuse me, at the end. So let's just hold on to that. Okay, why is my, something weird is happening on there. Okay, so what I want to talk about next is merge sort. So I got to go back to Paint so we can draw a picture. Oh, and I forgot to that's so strange. Way too many things to try to remember. I guess I should be organized and have like a list in front of me or something. Okay, so this is what was showing on the whiteboard when I was talking about the code that we wrote. So let me get Paint going so that we can talk about merge sort. Okay. Darn it, I should have saved that list of numbers from last time. So I don't know why it is, but like one of my things I hate the most in life is trying to think of lists of random numbers. 5, you know, without trying to do it without any sort of pattern to it. And every time I do it, the second number is always bigger than the first number, I've noticed. And I'll do it differently this time. 13, 6, 4, 19, 10, 27, 3, 1, 2, 3, 4, 5, 6, 7, 8. Nah, just one of each.
No, but it tested pretty well, actually. We looked at the same number.
Okay, so there's my 8 numbers. The way that merge sort is going to work is that the strategy here is sort of a divide and conquer strategy. So what we're going to do is we're going to split the list into 2 halves, sort each half by using the same method that we use to sort the big list. And then we're going to merge those 2 lists together again after we have them sorted. Okay? So part of the reason this is a good sort is that merging 2 already sorted lists together is very easy. I don't mean easy to write the code, but it's very efficient, right? So let's first of all just talk a little bit about how that might work. So before we dive into the big picture of how this sort works, I'm going to get into one of the details, which is how do we merge 2 lists that are already sorted. So if we have 4, 9, 13, 17, 21, and then we have 8, 11, 12, 18. How many numbers do I have there? 5. I'm going to have more in this list, I guess. There we go. Okay, so the way that we're going to merge these 2 is we're going to just create another list here, and we're going to have to go down each of these lists, comparing the 2 numbers that we're looking at, copy the smaller of the 2 into the new list, and move the counter down 1 in that array, right? So we can look at these 2 lists, and so I'm looking at this number and this number, right? Compare those 2. The smaller one is 4, and I move the counter up to the 9. Compare those 2. The smaller is 8. So I put the 8 down here and move that counter up to the 11. Compare the 9 and the 11. The smaller of those 2 is the 9, so I put the 9 in the new list, and then I move this counter up to here, up to the 13. Compare 13 and 11. 11 smaller, so put the 11 there and move this guy up. Compare 12 and 13. 12 is smaller, so I put the 12 in the new list and move that counter up. Compare 13 and 18. 13 is smaller, so I put 13 in the new list and move that counter up. Compare 17 and 18. 17 is smaller, so I put 17 in the new list and move that counter up. Compare 21 and 18. 18 is smaller, so I put 18 in the new list and move that counter up. And now at this point, you don't have to keep comparing because you're at the last item in one of the lists, and the item you're looking at in the other list is bigger than that. So at that point, you can just copy the rest of the numbers from the list you're not done with yet. So I'm going to copy down here I guess I did that one step too soon. Compare the 21 and the 24. 21 smaller, Now, when I increment this pointer, I go off the end of the list, and that's the signal for me that I can copy the rest of the numbers from the other list. 24, 27. Okay? So, give me a big O notation for that process that I just did. How many steps did that take?
Including the splitting, the sorting?
No, just the process that just that part of it, just the merging of those two lists. Now remember that if I have to look at the same item more than once, if I have to look at it 2 times or 3 times or 4 times, I don't really care about that, right? I only care about if I have to look at it like n times or something like that. Look at each item n times. So yeah, it's just going to be big O n. You're basically just looking at everything in the list once, or maybe twice or 3 times, but you know, close enough. So basically, anytime you see a situation where all you do is kind of traverse the list one way or another, that's big O n. And that's basically what we're doing here. Okay? So once you've got 2 ordered lists, merging them together is very fast. It's order n. Okay? All right, I think I've got to get rid of this picture now. What did I do? Oh, I have to make a white. No, I have to make a white square.
Use select.
Use select. Okay. Select a
Alright. Copy.
copy,
Paste it somewhere.
paste,
Now just grab a corner. Right.
make it bigger, and then move it down here.
Here it is. Right.
All right. Didn't we do it a different way last time too?
You can also select everything and then just press delete.
Select everything and then press delete. That would be a very fast way to do it. All right. Okay. I'll get this paint thing figured out one of these days, right?
Maybe class.
Sorry?
New class.
Yes. Right. Okay. So let me show you how merge sort's going to work. Okay? On this list of numbers, we split the list of numbers up into 2 separate lists. So actually, in this case, it might be better to put our lists in a box so we can tell that that's one of our lists. So we're going now to have 13, 6, 4, 19, and then we're going to have a separate list of 10, 27, 3, 1. And those are 2 separate lists. Okay, and just to kind of keep my thinking organized, I'm going to keep track of where those lists came from. Okay, so now I do exactly the same thing to these 2 lists that I did to the first list. When I describe an algorithm that way, there's something that should come to your mind. Recursion, right? Okay, so I'm looking at this list. The first thing I do to sort this list is I split it into 2 lists. So let me just start by getting all the numbers down here again. And here. Oop. Yeah. Nah. Okay, now I look at each of those 4 lists, actually, and I do exactly the same thing to those. So here's a list with a 13 and a 6 in it. The way I sort it is I split it into 2 lists. Now, we're kind of looking at this from a theoretical perspective, right? In the real world, you wouldn't take a list with 2 things in it and use merge sort to sort them, right? You would just compare them and switch them if they're in the wrong order. But let's just go with this for now. So same numbers, just further apart. 13, 6, 4. Oops, wrong. And okay, now we're at the point where we have to start merging lists. So, but before we do that, let's talk about how much time we've used up so far. So how many steps do you suppose it took to get through those 4 lines that I have there? So I guess that may be hard to answer because I haven't really said what I mean exactly when I say split it up into lists, into smaller lists, right? But basically these are going to be recursive calls, and all I'm doing is changing low and high. Right? We've done some recursive functions using arrays, and basically we don't actually send a different array back. We send the same array, but we change low and high. Okay? So to get from here to here, all I'm doing is changing the value of low and high. And then to get from here to here, same thing. From here to here, same thing. So basically this is pretty insignificant. If you really wanted to get technical, to get from here to here, it would be big O log n, because that's how many steps there are. There's 8 numbers here. It takes 3 steps to get to the bottom of this. If there were 32 numbers to start with, how many steps would it take to get to the bottom? 5, because 2 to the 5th is 32. Or to say that another way, log base 2 of 32 is 5. Okay? So what we've got out here is big O. Oops. Yeah, okay, maybe my O was a little too big. But, oh, sorry. Yes. Okay. All right. So let's start merging now. I'm going to try to make the distance between my rows smaller so this actually all fits here. Still going to have the same numbers, so 13, 6, 4, 19. But now, oh, that's not right at all. Right, when we merge the 13 and the 6 together, what list do we get? 6, 13, right? Because we're sorting them, we're merging them in sorted order. So we get 6, 13 there. Okay, and then when we merge the 4 and the 19 together, we're merging 2 lists together. Each list has 1 item. And so we get a list with 2 items in it, 4, 19. 10 and 27, 10, 27. 1 and 3, 1, 3. Okay? All right, and just so we're kind of thinking ahead a little bit about our analysis that's coming up, how many steps did that take to get from that pass to the next pass? From here to here? Well, for comparisons, that meant we're actually looking at each item here once, right? Basically, this is another one of those cases where you have to deal with each item in the list once, right? So it's, to get from there to there, it's going to be big O. Is that a big O? Big O, I guess so. Yeah. Yeah.
Yeah.
Okay? I don't like that O, it's too small, but okay, so let's keep going. So when I merge the 613 and the 419, I'm going to get a sorted list. Well, actually, you know, going from this pass here to this pass here was exactly what we talked about at the very beginning when I said, when I showed you how to merge 2 lists together and asked you what the big O of that was, right? That's all we're doing there. Forgot that we had already talked about that. And then merging the 1027 list and the 13 list together, I get 1, 3, 10, 27. Okay, and then I just actually let's actually note here that to get from here to here, there's another big O. Oh, I get it. That's why my O is little. I see. You guys had that figured out, and I was clueless. Okay. And then we merge these 2 together to get the final list: 1, 3, 4, 6, 10, 13, 19, 27. Did I skip something? Oh, not bad. Okay. And that step there is big O. Okay? So this process is not hard, okay? If you don't understand what just happened, it's because I didn't explain it very well, okay? I'm not saying I didn't explain it very well. I'm just saying, you know, this is not hard to get. If you don't get it, just make sure you get it because, you know, if I sat down with you for 2 minutes, I'm sure that you would get it. All right, so let's analyze this. Anybody want to take a shot at it? Don't just tell me the answer. Tell me how you get there. Sorry, analyze. Give me the big O. What's the big O of this algorithm? Yes.
So you're going to have to make n number of passes log of n number of times?
I'm going to have to make n number of passes log n number of times. I think that you're right, but I think you used slightly wrong words there. Because you said n each one of these to get from one line to the next is a pass.
Oh yeah, so n number of steps log n.
Right. So each pass is big O n. And how many passes are we going to need? Log n. So multiply those together. So altogether, this is going to be big O n. N log n. Okay? And actually you could say big O of n log n plus big O of log n, but as we've seen before, in that case, we don't really even care about the big O of log n. It's such a small factor in all of this, right? If you've got if n is 1,000,000, right? 1,000,000 times log n plus one more log n, you don't really care about that one more log n, right? So when we are wondering about the asymptotic running time, this adding in the big O log n doesn't matter. Okay, so let's think for a second about how big of a difference this makes. Okay, did we have this conversation when we were doing binary trees? The difference between n and log n. So let's say that we have 1,000,000 items in our list. And let's say that we are using bubble sort, which is we go in square. So how many steps is it going to take me to sort my list if I'm using bubble sort?
For how many items?
1,000,000. 1,000,000 items.
10 to 12.
So 1,000,000 times 1,000,000, whatever. So that's 10 to the 12th, a trillion, right? So 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's how many steps it's going to take. Probably not acceptable, right? So what does this turn into if I use merge sort instead? So it's going to be 1,000,000 times whatever the log of 1,000,000 is, right? What's the log of 1,000,000? This is a computer science thing that you should just know. 2 to the what is 1,000,000? 2 to the what is 1,000? So 2 to the 10th is 1,024, right? So, you know, if you take very many more computer science classes, I guarantee that will be like stuck in your brain forever. 2 to the 10th is 1,024. 2 to the 20th is 1,000,000 something. Okay, 2 to the 30th, guess,
Billion.
billion something, right? Because you're timesing it by 2 to the 10th each time, which is 1,000. So 1,000 times 1,000 is a million. So what's the log of a million? Roughly 20. Yeah. It's rounded to the nearest whole number. It's 20. So instead of whatever that number is, it's going to be 20 million, right? Okay? So that is a pretty significant increase. It actually brings it from something that's just not acceptable to something that's fine. Okay? Any questions about merge sort? Want to work on the code a little bit? Let's work on the code a little bit. So, for purposes of working on the code, I'm going to open a new file, and might as well make it a CPP file. Okay, so I'll tell you, no I won't, we'll see how it goes. Okay, so what parameters do you think we're going to need to do merge sort? No items? Remember that we're thinking we're probably going to be using recursion here. Low and high, right? So we know which part of the array it is that we're sorting. So really the way to describe this is that merge sort is a function that sorts a portion of an array. So we're going to have int start, int end. All right, so we think this is going to be a recursive function. Anybody want to take a guess at how many lines of code this is going to be? 6, 2, 3. Okay. Well, so we're actually going to merge the two lists together in a separate function. So that's going to be a function, just a function call. So what's our base case going to be? If we've got one item in the list, right? So in that case, start and end will be equal. Okay? And in that case, what do we want to do? Yeah, just nothing. So this is a void function. So if start is equal to end, that just means we're done, right? So this is one of those cases where we could say if start is equal to end and then just leave it blank and put an else, but that doesn't really make sense. You just reverse the condition. So actually, let me just spell that out. Instead of saying if start equals end, do nothing, else, and then here's my recursive case. Okay. I'm just going to do the equivalent code, which is if start is less than end, recursive case. Right? So I can get rid of this there. I'll leave it there just for a second in case someone wants to stare at it while I'm doing this. But okay, so we finished our base case. Now we just have to figure out what we do when we're not done. What do we do when we're not done? We're going to call merge sort with different values for start and end, right? And just speaking, don't use start and end or code or anything, but just speaking in terms of that picture, how are we splitting the list? We're splitting it by 2. Yeah, we're splitting it into 2 lists. Okay, and we're merge sorting both of those lists. So the first tab. Let's start with the first tab. Merge sort list what? Start. Does that look right? Not right. So, well, I mean, so what? Let me ask this: what if start is 20 and end is 40? Or no, start is 20 and end is 30. Does this give you the first half of the list? The first half of the list in that case would be between 20 and 25 or something like that, right? But n divided by 2 would give you 15. So this is a very natural place to go, but really that's assuming that start is 0, right? Really what you want is halfway between start and end, which is just another way of saying that you want the average of start and end. That make sense? So start plus n divided by 2. That make sense? Okay. And then we need to call merge sort again, right? On the second half of the list. So that's going to be start plus n over 2 plus 1, right? I don't need to send that same one for both lists. Plus 1 all the way up to n. Okay? So now I've sorted the first half of the list. I've sorted the second half of the list. Now what do I need to do? Merge them together, which we're going to call in a separate function to do. Done. Okay. So that make sense? Code make sense why that would work? Okay. Good. So merge actually turns out to be fairly involved. So not because it's hard, but because there's just a lot of details to take care of. So I might, I'm not going to belabor the point quite as much. I'm going to need a separate array because as I go through these 2 arrays, I'm copying each number down into the new array, right? So I'm going to have a temporary array there, which, by the way, is one of the downsides to merge sort. It takes up a lot of memory. If you've got an array with 1,000,000 things in it, and you just, okay, I'll just declare another array with 1,000,000 things in it, that can be a problem sometimes. And then I want to figure out let me think for a second. Okay, so I'm going to say I'm going to have a count. Oops. That starts at what? So remember, I'm treating this as when I merged the second. I sorted the first half of the list. I sorted the second half of the list. Now what I have is a complete list, but the first half is sorted and the second half is sorted, but it's not all sorted. Does that make sense? I've got a list that starts at start and ends at end, and what I know about it is that it may not be sorted yet, but all the numbers in the first half are sorted and all the numbers in the second half are sorted. So what I'm merging is the first half of the list with the second half of the list, right? So let's figure out where the middle of the list is. Okay, and that tells me that's how I figure out where the start and end of the two different lists is going to be. So left is going to be that. Remember, at the very beginning when I was drawing that I had the two lists that I was merging, and I kept drawing the little line above each one. Okay. Left is going to be keeping track of what number you are on in the first half of the list, and right is going to keep track of which number in the list you are on in the right half of the list. So where's that going to start? Okay, so remember, if this right here is my list, okay, I need to have two pointers. I'm going to call them pointers even though they're actually indexes into an array, but two pointers, one pointing at the number we're currently on in the left part of the list, and one pointing at the current number that we're on the right half of the list. And what I do is I compare those two. The smaller one gets copied down, and I move that pointer up. So in this case, I compare the 4 and the 1. I copy the 1 down to the temporary list, and then move the pointer from the 1 up to the 3. So left starts at start, right starts at mid plus 1, and then I'm going to say while left is less than or equal to mid. Okay, so while the left pointer hasn't reached the end of the left list yet, and right is less than or equal to what? End. Okay, so right hasn't reached the end of the right list yet. What I'm going to do is compare the two that they're pointing at. So if list sub left is less than or equal to list sub right, copy count, copy list sub left into the temp sub count. Okay, so count is the variable that's going to be keeping track of where we are in the new list that we're creating. And move the left pointer up one. Else, do the same thing in the other list. Okay, and then count plus plus, and we're done with that while loop. Okay, so in terms of sorting the two lists, merging the two lists, that's really like 99% of the work there, right? That while loop encompasses the whole process of comparing the two numbers, moving one up, comparing those two, moving the other one up, until you hit the end of one of the lists, right? So when we finish this while loop, we've reached the end of one of the lists. So what we have to do now is copy the rest of the numbers from the remaining list, the rest of the numbers from the other list, down into the temporary array. And we have to figure out which list it is that we need to copy from. And we could start by using an if statement to figure that out and then go into a while loop. But it turns out to be easier to just say while I'm still not at the end of my left list, copy those down. Oops. Okay, and then the same thing in the right list. And then what's going to happen is that only one of these two while loops is going to get executed. Okay? Just one thing left now. Anybody tell me what the one? Yeah, I need to copy that temp array back into the original list. And I'm going to need a for loop to do that. Okay, so that's a pretty involved function. I think what it's doing is conceptually pretty easy. That's the first thing I talked about today, merging those two lists. But it turns out to take a lot of code to do it. Okay, you're not responsible for understanding this code or reproducing it. But for one thing, I think it's fun. I don't know, maybe I'm alone there. But for another thing is, if you really do get this, it'll come in handy sometime if you're taking more computer science classes. So you might want to just take a close look at it. All right, let's take a break. And then when we come back, we'll do another sort. All right, let's look at quicksort. Quicksort and merge sort are the two sort of classic efficient sorting algorithms that we look at. And quicksort turns out to be sort of the opposite of merge sort. The things are done in an opposite order from merge sort. So in merge sort, nothing gets sorted at first. You just keep dividing and dividing and dividing, and then you start sorting, right? With quicksort, so with merge sort, the first thing you end up with is two separate lists that are both sorted. With quicksort, what you end up with is two lists that where everything in the left list is less than everything in the right list. And then you have to just sort the left side and sort the right side. And then you're done. Okay? So I'm going to go through this twice, once really fast at a very high level, and then I'm going to go back again and show you a little bit more of the detail of how the algorithm works. But basically what we do with quicksort is we pick a number, and then we put all of the numbers in the list that are less than that number on one side, and all the numbers less than or equal to, all the numbers that are greater than that number on the other side. Okay? And the interesting part about this, like if you were going to study quicksort and how to improve it or something, really the most interesting question is, how do you choose that number? Right? Because if you choose that number poorly, quick sort can turn into a really, really bad sort. So there's lots of different, that number is called a pivot. And there's lots of different techniques for how to choose a good pivot. But what we're going to do is something just very basic and easy. I'm going to just use the first number in the list as the pivot. Okay? Another almost as easy way to do it would be to look at the first two numbers in the list and average them and use that as the pivot. So then you'd maybe be a little bit less likely to accidentally just choose, you know, the biggest number in the list and use that as the pivot. Because what you want is you want to pick a number so that about half of the numbers will be less than it and about half the numbers will be more than it. Okay? So anyway, I'm going to choose 13 as my pivot. So after one pass, I'm going to have all of the numbers less than 13 on one side, and I'm going to have all the numbers, actually I think we say less than or equal to, and then I'm going to have all the numbers greater than 13 on the other side. Okay? This happens to be a situation where averaging the two would have been better, huh? Because we ended up with a pretty lopsided list. But let's just go with it. All right. So now we do the same thing again to each of these two lists. So we pick a pivot of 6. And I put, actually, let me stop and get organized a little bit. Okay, so I'm picking 6 as my pivot. So all the numbers less than 6 are going on one side. Less than or equal to 6 are going on one side. And all of the numbers greater than 6 are going on the other side. Okay? 19 is going to be my pivot. So, well, hold on. Let me finish this first. Okay. 19 is going to be my pivot. So we can look at this list and say, well, why don't we just stop because we're done, right? But the algorithm isn't going to be able to figure that out. So we're going to choose 19 as the pivot. All the numbers less than or equal to 19 go on one side, and all the numbers greater than or equal to 19 go on the other side. Okay, so we're done over here on the right. On the left, I'm going to choose 4 as the pivot. Bummer, I'm going to end up with, anyway. That's not a very good pivot, but that's what we're stuck with. So 4 is the pivot. All the numbers less than or equal to 4 go on one side. All the numbers greater than 4 go on the other side. And then with the 10 and the 13, 10 is the pivot. All the numbers less than or equal to 10 go on the left. All the numbers greater than or equal to 10 go on the right. So here's where it starts getting important to actually draw the squares, right? Oops, that didn't work. Oh, wrong thing. Wrong tool. Okay, and it's probably going to be best for purposes of our illustration to bring these down. Okay, so looks like this is turning out to be, our pivots are not working out very well. I should have done the averaging technique. Oops, that's not what I meant to do. So now 3 is the pivot here. So I'm going to put everything less than or equal to 3 on one side, and everything greater than 3 on the other side. And then I'm going to just bring everything else down. And just because I know that you guys love watching me do this over and over again, we have one more step to go. Let me just pause for a second, and I think I mentioned this before, but I just want to be clear. So we're drawing this picture here. Each line that I'm drawing is representing how the array is changing after each pass through the array, right? So it's not like I have all these different arrays here. This is one array, and these are snapshots of the array. Okay, but I think it's a pretty good way to visualize it. So I think for purposes of our illustration, it's probably going to make more sense for me to just fudge this a little bit and say that let's say that the 1, 3 is done. We sorted it. We could say that anyway. We're just going to fudge it. Okay. So what's left now? Sorry?
Combine them all together.
Actually, as it turns out, we're done. Yeah. Right. So even though conceptually I'm thinking of these as a bunch of little lists here, really they're still all in one array, right? So really we're done once we get to that point. Does that make sense? Okay. So I think you know by now that each pass through the array is big O. Each pass through the array, so getting from here to here is, I guess I shouldn't assume anything. Big O, N, right? Okay. So the only question left is how many of these steps are there going to be? If there are N items, how many steps are there? So it's a little trickier this time than it was with merge sort, because with merge sort we could always divide them equally. With quick sort, the discussion is a little more complicated because it's not clear if we're always going to separate them equally or not. In fact, it's clear that we're probably not going to always separate them equally. So let's talk about that. What do you suppose would be the worst case scenario for how many steps there would be? Can you imagine what the worst case scenario would be? So explain to me what it's going to look like. You know, why would it be n squared? So the best case scenario, go ahead. The best case scenario would be if I split the list into exact halves each time, right? So what would the worst case scenario be?
Don't split it at all.
So I split one number.
The worst case scenario is you get one number in one list and the rest of the numbers in the other list each time, right? And so if you do that every time, how many passes is it going to be? N, right? So worst case scenario, this ends up being an n squared sort. N to get through one pass, and n passes, so n times n. So in the worst case scenario, quick sort's pretty ugly. Okay? Let's talk about the best case scenario. Okay, best case scenario would be we split it exactly in half each time. How many passes are there going to be? I didn't hear. So, no. Well, I mean, in this case it is, right? But if I have 16, so let me put it this way: if I'm lucky and I divide the list exactly in half each time, then I'm dividing it exactly the same number of times I did with merge sort, right? Splitting it in half each time. So if there's 8 of them, there would be 3 passes. If there's 16 of them, there would be 4 passes. So how many passes would there be? Log n, right? Okay. So basically, anytime, even if you're completely mystified by all this talk about log, anytime you see a situation where you're dividing stuff in half over and over again, that's just log n. That's why the searching in finding something in a binary tree was log n, right? Because every time you look at a node, you eliminate half of the tree. Okay. So each pass takes n. There are log n passes. So best case scenario, this whole thing is what?
N log n.
N log n, right? Log n passes, each pass takes n. So you multiply n times log n. Okay. I said I was going to do it really quickly the first time and then go into more detail. That was my really quick one, so now we have to do it in more detail. So what? Oh, log. Okay. So I'm getting into the detail about how you're actually going to do this in your code, is what I'm doing. How are you going to put all the numbers less than or equal to the pivot on one side and all the numbers greater than the pivot on the other side? We're going to have 2 pointers. Is it okay that I call them pointers? Is that confusing? They're really just indexes into the array, but when we draw the picture, they're pointers, right? So a pointer starting at the bottom and a pointer starting at the top. Okay? So what we do is pick a pivot. So actually, no, let me do it the other way this time. Let me do the average of the first 2 as the pivot. Maybe that'll give me a little bit better division. So the average of 13 and 6 would be 9. 13 plus 6 divided by 2, 9. So what I do is I start with, on the left side, I move the left pointer up until I get to a number that is bigger than the pivot. it already is, so I'm done. I move the right pointer down until I get to a point where it is less than the pivot. Sorry, until I get to a number that is less than the pivot. That's already true, so I'm done. And then I swap those two. One, 13. And I move the left, and then I do the same thing again. Move the left pointer up until I get to a number that is bigger than the pivot. So not 6, not 4. I move it up to the 19. Move the right pointer down until I get to a number that's less than the pivot. Well, just move it once, and I found one. And then swap those two. Okay, and it turns out that the 6 and the 4 are just going to stay there. So swap the 19 and the 3. Okay, then do it again. Move the left pointer up until I get to a number that's greater than the pivot. So that puts me at the 27. Oh, it puts me at 10, sorry. Pivot was 9, so that puts me at 10. And then on the right side, move down until you get to a number that is less than the pivot. So that actually is going to just send me all the way down to the 4. Okay. And then what I do is, so I'm doing this in excruciating detail, okay, this is so you know how it's going to stop, okay? And then, so what I do, I only swap them as if left is still less than right. That makes sense? So because they crossed, I'm not going to swap them, and I'm just going to leave them alone, which means the 10 is going to be there, and the 27 is going to be there. Okay? So what I have is a list where all the numbers are less than or equal to 9, and a list where all the numbers are greater than 9. Okay? And then that same process again. I will do a little bit of it and see how quickly it goes. I may just punt it if it's too tedious. But so the pivot here for 1 and 6 is going to be 3. So I'm sorry. So for this, you know what? Actually, I don't think I'm going to go any further. I think you guys got it. Okay. Because you got the quick version where I thought I did it all the way down to the bottom. So all I was doing here was just showing you one of those steps in more detail. Okay. So let's think about the code for a minute. Okay. So maybe it'll help to have this up there, I don't know. Boy, quick sort, what am I going to need? Yeah. Same thing, right? Quick sort, I'm going to write it to be a function that sorts a portion of the array between left and right, inclusive. Okay, base case. Left and right are equal. In other words, there's one item in the list. So this is exactly the same situation. I'm not going to write if left is equal to right. I'm going to say it as my recursive case. So if left is less than right, that means I need to keep going, right? What do I do first? Right. So actually, say again? Okay. So yeah, the first step is to get the pivot, but what I'm going to do is I'm going to relegate the whole process of getting a pivot and moving the numbers around to another function that does one pass. So one pass is going to be in a separate function that I'm going to call partition. Okay, so that function creates, takes the portion of the list between left and right and divides it into two lists that have all the numbers, have all the numbers less than some pivot on one side and all the numbers greater than some pivot on the other side. Okay? Then what do I do? Call quicksort on each half. Quicksort list left. Okay, so this time we don't know. We have to have some way of knowing where the partition function divided it, right? So what we're going to do is we're going to have the partition function tell us that. That easy? So we're in this function, we're sorting a list that's between left and right. And so what we do is we call this function partition that puts all the low numbers on one side and all the high numbers on the other side, but we don't know where the division line is between them. So we need to have that function tell us where the division line is between the low numbers and the high numbers. Okay? And the way I'm going to do that is I'm going to actually have it return that number, which violates one of my style conventions, but I'm going to do it anyway, okay? Because I don't want to rewrite my code on the fly. Okay? So pivot, when I say pivot there, that doesn't mean the number that we used as the pivot. That means like the index of the middle point. So maybe that's a confusing thing to call it. Let me call it middle or divider or something. Any ideas? Divider index. Okay? So now actually, let me digress just for a second. I think probably if you look at the algorithm formally, I'm trying to think about this. I may be using the word pivot slightly. I'm not sure if the word pivot actually means what I've been saying, which is it means the number that you're going to use as the number to compare everything with, or if it actually means the index of where that dividing point actually ends up. Because really when you think about a pivot is something you pivot around, right? So really it would make more sense to say that it's the location of the middle. I don't know. It could be either way. Okay.
Because you're swapping the numbers.
Yeah. Makes more sense. Yeah. Okay. Right. Okay. So we're doing quicksort on the list between left and divider index, right? Hold on for a sec. No, we want to know the index of the left and the index of the right for the new list, right? And then we're going to quicksort list right divider index. No, right. Divider index plus 1 Right. Okay. And we're done. How's that look? Any questions about that? Divide the list into two. Sort the left half, sort the right half. Done. Except we still have to write the partition function, right? Which, once again, turns out to be the hard part. Or, I don't know if it's the hard part, but it involves more code. So for this, I'm going to actually just use the first number in the array as the pivot. And then I'm going to do something else which is a little hinky, but I'm going to say while true. Because what I'm going to do is when left gets greater than right, I'm going to just return the pivot. Okay. Left. So I need a loop that looks at the left and moves left up until it finds something that is less than the pivot. So while list sub left is less than pivot left plus plus, and then the same thing on the right, while, whoops, I'm missing a parent up there, list sub, wow, while list sub right is greater than pivot right minus minus. Okay, so now I've got it so that left and right are pointing at things that need to be swapped, unless they've crossed, right? So if left is less than right still, then I just want to swap list sub left and list sub right. Else, what do I want to do? Return. No, return. I want to return whatever the index of the pivot is. Turns out that we can send right. We can return right. Yes.
So, what's up with the while true?
Meaning, well, what do you mean by what's up with it? Why does it work, or why am I doing it that way?
Why would you do that if it's never going to be false?
Well, because I'm just saying, it's all. Eventually, this is going to get executed.
Oh, okay.
Right. So I'm just saying, keep going through, and I could write it differently, and I probably would, but I probably borrowed this code from someone and never actually fixed it the way that I would do it.
Just going until you hit that return.
Yeah, I'm going until I hit this return. Okay. Okay, so that's the code. And so the reason that I show you the code, and you tell me if I'm just like full of it here, but when I'm in your position, actually seeing the code helps me understand the algorithm a lot more. Like when I draw a picture of it and I'm moving stuff around and drawing lines and stuff, I can reproduce that, but it's hard for me my brain to go from that sort of more theoretical level to actually what's going on, how the computer is making it happen. So I just want you to have at least a little bit of a sense for how the computer is actually going to make these things happen. So we're out of time, so what I'm going to do is we'll actually see all of these sorts in action next time. Okay?
Could you just put, no, instead of true, could you just put while left is less than right?
Yeah, I could put while left is less than right,
And then just have your else statement outside before the while.
and then just not even have an else there. But
What? Why won't it execute?
Uh-huh.
Because it'll eventually hit that return.
let me.
Which exits the function.